Welcome everyone to our talk. I'm Sohail, and today I'm going to present our work SLGPT, where we use transfer learning to generate Simulink model files with the goal of finding bugs in Simulink toolchain. When designing complex cyber-physical systems, engineers often use commercial toolchains such as Simulink, where they prototype their system using graphical block diagrams. A real-world example of such a system would be a component of a McLaren supercar where its charging system was designed using Simulink. Typically, engineers use the toolchain itself to automatically generate codes and executables that can be directly deployed in the target hardware. As these executables are often deployed in safety-critical systems, it is important that we eliminate bugs, as at worst, a bug in the toolchain may propagate to the artifacts they produce. A quick background on Simulink. The basic component of a Simulink model is a block which can represent equations. The block have connections between them through which data flows. Simulink by default supports many block libraries, which is analogous to libraries in any other programming languages. To deal with increasing model size and complexity, blocks can be grouped together in a subsystem or in a separate model. Coming back, finding bugs in Simulink is hard, as its code base contains millions of lines of code, and it does not have a complete publicly available formal specification, which can be partly attributed to its commercial nature. First, we explore if we can use deep learning approaches to automatically learn the language features and generate Simulink models. Language models are one of the promising avenues for random model generation. Language modeling at its basic is the task of predicting the next words given a sequence of previous words. An example would be given a sentence such as "what time is it?" The language model should be able to predict a question mark as a next token given the context. DFuzz-SL is the first work that attempts to learn a language model for Simulink. DFuzz-SL basically leverages textual representation of the Simulink model files, the one you see on this slide. Quick note here, even though the Simulink model files looks like human written code, these files are internally created by Simulink, and the end user only uses graphical user interface or APIs to create the model. Having said that, DFuzz-SL essentially portrays the Simulink model generation as a natural language generation problem. To do that, it trains a long short-term memory neural network that is then used to generate Simulink models and test the toolchain by detecting if the generated model causes Simulink to crash or not. DFuzz-SL was able to find 2 confirmed bugs in Simulink and reported a high valid model generation rate. But since training a deep neural network requires large training corpus to generalize, and as there is no such large Simulink model corpus readily available, it trained the LSTM on a relatively small size, homogeneous, randomly generated models. Another aspect it overlooks is the fact that even state-of-the-art language models have limited context window, and it may not be able to capture long-term dependencies. An example would be if 2 adjacent blocks in Simulink model appear further apart in the model file, then the language model may not be able to capture that dependency. So since training from scratch is very expensive, a relatively new way in natural language processing to address such an issue is to use transfer learning. The intuition behind transfer learning is same as how a human would learn. We as humans don't learn everything from scratch, but rather reuse or transfer our old knowledge to learn new things. Transfer learning in NLP involves pre-training, where we train a model on a source task, which has sufficient training corpus, and then use such a pre-trained network to fine-tune it with the target task dataset. For example, we can pre-train the neural network on a dataset that has programs from any programming language, from which it can learn program structure, data flow, and so on, which can then be used to fine-tune on Simulink language. So this is the overview of our tool SLGPT. SLGPT is the first work that uses transfer learning for generating graphical block diagram models. First, we collect a training data set from a random model generator, SL4s, as well as mine open source repository. Then we rewrite and restructure the Simulink model while making sure that the training corpus only contains valid or compilable models, which is then fed to our pre-trained neural network. The fine-tuned neural net is then used to generate models, which is finally used to test if it crashes Simulink or not. We first use SL4s, which is a random model generator for Simulink, to generate about 1,000 models. At this stage of the project, we only experiment with small models having less than 60 blocks and does not have any hierarchy. You can see an example of SL4 generated models on the slide. We also mine open source repositories such as GitHub and MATLAB Central, which have a large number of Simulink projects. Since GitHub does not recognize Simulink as a programming language by its API, we rely on Simulink as a search keyword. And for MATLAB Central, we use their RSS feed to mine Simulink projects. Our mining tool automatically finds Simulink projects without having to download them manually. Since we focus on flat models only, we have about 400 real-world models by mining these repositories. Moving on, since we don't want the neural network models to learn unnecessary rules, we either remove or rewrite the Simulink model files, such as removing extra white spaces, comments, and we also rewrite block names to short but unique names to limit the token in the resulting file. To match the learning style of state-of-the-art language model, we restructure the model file in a breadth-first search manner. So this is how we restructure the model file. So given we have a Simulink model represented by this block diagram, Simulink internally stores this information in a model file where it has all the block definitions followed by its connections. Our restructuring algorithm first creates two sets of blocks. S contains blocks with int degree equals to 0, and B contains all remaining blocks. We traverse the given block from the S set in a breadth-first manner. Whenever we visit a node, we add the node along with its connection in the model file until we cover every other node. So here is an example of a actual Simulink model and its corresponding model file. Note that the model file has over 1K lines. SLGPT's code restructuring and rewriting steps compresses the representation to about 50 lines. Because of the code rewriting removes position information, all blocks are superimposed. Then we use generative pre-trained transformer 2 from OpenAI, which has been trained on 40 gigabytes of English text. GPT-2 model is based on transformer architecture, which is shown to be superior to LSTM for language models, as it can process sequence as a whole while learning the relationship between tokens in the sequence. Whereas in LSTM, long-term context may be lost as it processes words sequentially. Another advantage is GPT-2 uses byte-pair encoding to construct its vocabulary, meaning all Simulink model file tokens can be mapped to the GPT-2's vocabulary, so there is no out-of-vocabulary tokens. And it also has a large context window. So once GPT-2 has been fine-tuned on Simulink models, we generate new models by seeding it with model keyword and sample token by token. We use the best performing sampling strategy from DeepFuzz SL on SLGPT, that is the top P sampling. So how this works is we first seed the fine-tuned GPT-2 with model keyword. The model predicts likelihood of the next token in its vocabulary. We then sort such probability distribution in descending order. Given P equals to 0.75, we take only those tokens into consideration whose cumulative probability adds up to the P's hyperparameter value. In the example, 5 tokens probability highlighted by the red box adds up to 0.75. We then perform a multinomial experiment on it. We do this to make sure that there is variability in the generated models. If the experiment produces a special token, SLGPT marks the models as completed. Otherwise, we append it to the seed text and continue the cycle. Coming to the experimental setup, we use TAC, which provides high-performing supercomputers to fine-tune SLGPT. And we fine-tune the SLGPT in 2 collected datasets separately. So first, we compare SLGPT with DFuzz-SL on its ability to generate valid models, as well as how structurally similar the generated models are to the training dataset. The results show that SLGPT consistently produces about 43%, 40 to 45% valid models, regardless of the dataset it was trained on, while DFuzz-SL relies on the homogeneity of the training corpus to generate compilable models. So here are 3 examples of Simulink models generated by DFuzz-SL. You can see that most of the models are connected in pairs and do not really resemble how a human would design a Simulink model. On the other hand, the SLGPT generated models are closer to how a human would design a Simulink model, which can be seen in these examples. Furthermore, we looked at certain graph properties of these Simulink models in the training data set versus the generated models. Here you can see that 90% of the real-world models in the training data have less than 17 blocks in them. SLGPT generated models respects the distribution of the model size and closely align with the training data. On the other hand, DFuzz-SL is endlessly generating blocks in the model. Similarly, we looked at a number of connected subgraphs per model. In real-world model, majority of models have one connected subgraph, meaning all blocks are connected to one another. In this case, too, SLGPT generated model follow the distribution more closely to the training data than DFuzz-SL, as you saw on the example generated models previously. As around 85% of real-world models also have source block to sink block connections, we also look at if such connection exists in the generated model. As you can see, DFuzz-SL fails to have source to sink connections, but SLGPT manages to capture the distribution of majority of the models, as training data have between 2 to 10 number of blocks between a source block and a sink block. Moving on to our second research question, SLGPT reproduced the bugs found by DFuzz-SL. The bugs occur mainly due to a misconfigured port in different blocks, which causes Simulink to crash when compiling. While DFuzz-SL only found bugs in signal-generated blocks, SLGPT found bugs in a wide range of Simulink library blocks. SLGPT also found a unique bug missed by DFuzz-SL. On the slide, you can see two types of scope block from the Simulink library with appropriate parameter configuration. SLGPT generated a model whose floating parameter is set to off while setting its port to 0, which crashes the Simulink 2018B version. The bug has been fixed in later Simulink releases, where Simulink basically rejects such ill-configured blocks. So in conclusion, SLGPT is the first work that uses transfer learning to generate graphical block diagrams, and all the evaluation data and source code are open source on GitHub, while training data is on Zenodo. So lastly, I want to thank DAC, NSF, and MathWorks for providing resources and funding the research. Thank you.